Poisson structure which you pulled from the Borel subgroup. And now you speak about the Gaudin system. So can you please explain the relation of Toda
it will be the next. It will be the next step.
So then, what do you call the Gaudin structure? I don't know this.
The statement was the following: that if you consider the Lax operator with the full A matrix with the values in SLN, the Deift Hamiltonians, the Deift functions commute with respect to the complete Poisson structure.
Complete Poisson structure on SLN.
SLN.
Dima,
So you just consider.
I'm sorry, I a little bit confused. Why you call the system Toda system? Your phase space is a space of symmetric matrices?
For the moment, no, not.
Could you please point out what is the phase space and how many integrals of motion you have?
I asked you to wait a few minutes. I will explain all the ingredients of the construction. I'd like to apply the standard Adler-Kostant-Symes scheme for the initial Gaudin model to obtain the full Toda system.
Gaudin model is the model that you propose to this Lax operator.
Yes.
With one pole. With
only one pole and the magnetic term.
Magnetic term is the anti-diagonal matrix.
Yes, very particular magnetic term.
Okay, it's somehow related to another model which you call Toda model.
Yes, but it's the next step.
Okay.
But the first statement is clear. The functions on the SLN matrix, like in Deift approach, compute with respect to the initial SLN Poisson structure. The next step is the Adler-Kostant-Symes scheme, and I will explain you a version of the following.
Can you give us the proof of this lemma? Will there be the proof or not? Or just...
it is quite familiar. So the characteristic polynomial of the Gaudin model produce the Hamiltonians of the system. So all the coefficients of these polynomials commute with respect to the Poisson structure.
So just
it's
this
a consequence.
Deltas.
But the next step is to observe that some asymptotic term of these components are related with the Deift Hamiltonians.
Sorry, just don't understand. So deltas are the coefficients of the composition of the characteristic polynomial with respect to epsilon, aren't they? Can you repeat the definition of deltas here so they can compare this with deltas?
So this is the definition of delta. But in fact, I demonstrate that even polynomials, all the polynomials pki commute with respect to the initial Poisson structure in.
But
for the
the Poisson structure is different, right? The Poisson structure is just the structure on.
Yes, yes, but it's okay. It will converge.
And so, how do you demonstrate that they commute?
Sorry, the lemma.
How do you demonstrate that the coefficients of how to demonstrate the lemma, right?
So the important statement is this one. So it is a relation between some asymptotic terms in generators of the Gaudin Hamiltonians and the Deift
Sorry, what are Gaudin Hamiltonians?
Gaudin Hamiltonians are the coefficients of its spectral curve.
With respect to epsilon?
For every value of epsilon.
And why do they commute?
It's some result from the theory of Gaudin model.
Oh, so this is just a kind of black box. Okay, thanks.
No, it's very simple, but it's a subject of some demonstration. So the statement is.
I mean, that is the black box for this particular talk. That's probably
Yes,
the subject
yes,
of
yes.
different talk. Okay.
It's not complicated, but it depends time. So the important thing that for every value of epsilon, this is a generating series of the Hamiltonians, and then the lowest term in expansion in epsilon else commute. That wasn't important. Okay.
Yeah, sure.
The next step is the Adler-Kostant-Symes scheme, which is a general method to produce integrable system from the simpler ones. So it is the following construction. Let an algebra G, Lie algebra G, be the sum of two its Lie subalgebras. And subject to this decomposition, the symmetric algebra of G may be also represented as the sum of subspaces G plus, G minus, S of G. And now I will denote by I the projection. Lemma states the following: let f and h be G plus invariant elements of this symmetric algebra G plus, and be commutative with respect to the standard Poisson structure in G. Then the projections commute with respect to the Poisson structure in G plus. Is it familiar, or you'd like I show this statement, Gosha?
This seems to be much simpler than the previous one, so
okay.
I wouldn't ask.
Okay, so it's a statement, and another statement is the following: that delta ki are G plus invariant. So I should say that in my case, I use the decomposition of GLN as B plus and SON Lie subalgebras. And so the choice of the magnetic term in the Lux operator of the Gaudin model was adapted to demonstrate the invariance with respect to the action of the Barry subgroup. So it's quite technical, but readable and quite expectable statement. And by this simple observation, I obtained that the restriction of the K on G plus substitute a commutative family.
May I ask about the first lemma?
The first lemma, yes.
So the conclusion of the first lemma, what is the first term in the Poisson bracket?
First term in the Poisson bracket?
Yes.
I don't understand.
Just what is written there?
It is the projections of F and H you see I goes from S symmetric algebra of G to the symmetric algebra of G plus. So I of F, it is a symmetric element of the symmetric algebra of G plus, or a function, a polynomial function on the dual space to G plus.
Okay, now I understand. It was not clear to me the letter, what is applied to F, it was not clear to me. This, you applied I to F. Okay.
I applied to F, I applied to H, and the Poisson structure as element of S of G plus commute
Okay.
in involution. So the space of such functions restricted to G plus substituted commutative family. There is some subtleties in counting their numbers, but principally they are of n minus 1 over 4, and which is asymptotically the half of the dimension of this phase space. The next step is the way to quantize this system. And there is some simple way using the quantization of the Gaudin system. The standard method in this case is the following. We consider matrix A, which is also the sum of elements of this type, Aij, are now functions, are now elements of the universal enveloping algebra of SLN and JLN for simplicity. And we can produce also the set of commutative commuting elements in the universal enveloping algebra. To do this, we have to consider the quantum determinant of the element A z epsilon minus dz. There, dz is the operator of partial derivation respect to z. I need to say what is the quantum, what is the determinant in this case, and it is determinant is the, for example, it can be calculated B Now, this is what is called the completely symmetrized non-commutative determinant. It is the same thing as
So are there signs in the formula? I don't see signs.
Yes, surely. Thank you. Thank you very much. So the statement is the following, that this determinant...
So it's -1 with the power of what?
-1, it is the sign of the product of sigma and tau. It is another way to calculate the determinant, which is efficient in the non-commutative case, because we use all possible orders of multipliers in each term of the determinant.
So isn't it just the full symmetrization of the
Yes.
usual determinant?
Yes, absolutely.
Mm-hmm.
And I will present the determinant of my Lax operator also in the similar form. So it's the sum of Q I K that dz epsilon. And I will look for the asymptotic of so each term here, it is also some homogeneous expression in the first two variables. Homogeneous. It is surprisingly well defined because the relation between these two variables is homogeneous, which is not right between z and dz. So Q I K also has an expansion in epsilon, and minus k minus 1 over 2 Q I K 0 1 over z dz plus O of epsilon. And the analogous statement in the quantum case says that Q I K 0 1 z dz it is some polynomial in z and dz, so we should expand it on, for example, as the sum of Q I K 0 I I suppose it should be some 1 over z k minus I and then the coefficients of these polynomials substitute a quantum commutative family. So the quantum Adler-Kostant-Symes scheme here, here is analogous. So I represent the Lie algebra SLN as the sum O n, and U SLN as U B plus O n U SLN. To do this, I need to choose some normal ordering. But principally, it could be done. And then I use also a projection from U SLN to UB. And I will denote the images of this projection as A plus in UB. The action of B on the generators of our commutative family Q I will denote them a little bit simpler manner, ki. So the q I k 0 I. They are the action lemma. Let X be an element of the Borel-Lie subalgebra, and then its action on Qi Ki. It is some character X Q Ki. So, and this character depends only on the first index. So it's give some idea of homogeneity of such generators, and then I have a series of some technical lemmas, but let M be a monomial in UB, and then Q Ki, then M A at K M is a product of BI K BI. Okay, and then the lemma, which is an analog of the Adler-Kostant-Symes lemma, it is the following. Let Qi Ki is a which is represented by the sum of positive and negative part, and the same is true for another generator B minus. And then the statement is the following: A plus at K B plus at L A plus. So this statement is an analog of the Poisson commutativity in the classical case, in this quantum situation, and it has some consequences. So I need to consider localization of my quantum algebra. Localization of U S L N with respect to the multiplicative set, multiplicative set of Q I K n minus K of all the highest elements of my polynomials defining the quantum integrals. So there is a statement that lemma S is a right order set. I'd like to recall the definition. S is a right set if or a set in an algebra A first point, and the second point about the divisors of zeros, but they're not important in our case. So it is a condition that if there is an analog of the left the left divisor of zero, then the same is true for the right multiplication. So both conditions fulfilled in our case. If we consider the multiplicative set generated by the highest coefficients of polynomials, and this allows to define the correct localization of our non-commutative algebra. Correct means that it is flat in some sense. So it's a good deformation of the commutative localization. So in our case, the quantum algebra is a localization of the quantum algebra. It is a localization of U B with respect to the set multiplicative set S, and the theorem says the following. The set Q I K I K n minus K is a commutative family in A in this localized algebra, and is a quantization of the classical full Toda system. So this is the old statement which I'd like to present you, and now I wish to discuss some geometric and algebraic application of this model. So the first geometric object related to the system is naturally the flag variety. It appears in the classical, in the context of the classical models by the following observation: the symmetric matrix can be represented. So it can be represented in this form. The psi is an orthogonal matrix, and lambda is a diagonal matrix. And that's why this system can be thought as a dynamical system on the flag variety, because psi, in fact, can be thought as an element of the orthogonal group divided by the group of diagonal matrices which act trivially on lambda, and this is exactly the flag of the variety of full flags in the AN case. The dynamics of the Toda system on the flag variety is very interesting from the geometrical point of view. So, for example, the the decomposition of the flag variety in the double Bria cells respect the dynamics of the system. So these Bria cells are invariant submanifolds with respect to the Toda flows. And there is a lot of results which applies the presence of these dynamics in description the geometry of these Bria cells. So it is some application of the theory of integrable systems to the geometry, to the description of the geometry of some very important manifolds. Another very important ingredient in this story is that double Bria cells are cluster varieties. Is the result of Bernstein, Femin, Zelivinsky. And for example, they are Poisson cluster varieties. And the relation between the Toda flows and the Poisson structure, this Poisson structure, very important.
I'm sorry, is this true for real or complex Bria cells? I mean, this cluster structure, because
now
I always imagined that cluster
now I'm talking about
with
the real structure in the AN case.
So double Bria cell is the intersection of usual Bria cell and dual Bria cell.
Yes, surely.
Okay.
There is another very important appearance of the Toda system in cluster varieties. So I'd like just to recall some result of Sasha Shapira. Shapira and Gus Schreider. They examined the cluster transformation in cluster varieties related to the to these double Bria cells, but in some particular case.
Sorry, is this Schrader or Schreider? Because remember, Gus Schrader was a disciple of Reshetikhin. Is this the same man or different? Because there's only one letter difference. I just wonder whether they're the same or not.
Just a moment. Yes, thank you. Very important.
Just to make sure that I understand what you're speaking about.
How you pronounce? Schroeder.
It's German, so I think it should be something like Schroeder. Schroeder, I don't know.
Okay, so they interpreted some series of cluster transformations as quantum Coxeter-Toda Hamiltonians, and the cluster transformation on the same cluster variety. So I'd like to write it down. A series of cluster transformation on B so this series of cluster transformation, which return to the same seed of the cluster variety, they appeared to be Poisson preserving, and this transformation they are was interpreted as quantum Hamiltonians of Coxeter-Toda system. And there is another, for the first time, textological coincidence of words. So the theory of quantum cluster varieties, cluster algebras. So it is a subject of it is the theory of the same subject, if you want. So it is based on the paper of Berenstein-Zelevinsky, if I'm right, of this of 2004, and they propose the version of quantum cluster algebras with the same questions about quantum Breuer decomposition, coordinate rings of quantum groups, and I suppose it could be related with the quantum Toda system. So principally,
sorry, can you give a very brief explanation what are Coxeter-Toda system?
it's better
Just
to
one.
look in the paper of Shapiro.
So can you give the reference?
Yes, but not now. Principally, this is all what I plan to talk about. It would be fantastic to discuss some moments, some propositions.
So first of all, I just would like to see the reference. If it is possible. I think this is already now, isn't it?
Okay. It's done.
Sorry, could you please say some resume of the talk? So what is the result?
The result was the same as 10 years ago. So it is a way to quantize the full Toda chain, full Toda system, and the idea why I proposed this title of the talk was the following: the way how it was obtained, the way of localization of the universal enveloping algebra resembles a lot with the localization produced by the Retech quasi-determinants, and the way how the quantum cluster algebras are introduced now.
So may I also ask another question for another reference? I'm sorry. I mean, this BFZ, Berenstein-Zelevinsky paper.
Yes.
I think I read this paper. It's some big paper of 2004 about, isn't it? About
Berenstein-Zelevinsky or
BFZ, the one which you mentioned just above.
It's a Bible
this
in cluster
rather.
algebras, yes.
I mean that. So it is dated by 2004, isn't it? What is the date of this paper?
I could give you an exact reference. Just a moment.
Oh, that would be very nice. Very kind of you.
It is of 96.
96, even before that. Okay, thanks. It's also available in the archive, isn't it?
So sorry?
It's also available at the archive.
Yes, I suppose, yes.
Okay, thanks.
Thank you very much for attention.
Thank you. It was very interesting. Okay.
Bye.
Thanks.